Yes. All right. Cool.
Oh, good.
All right.
All right. Are you ready to go?
Yes, sir.
I can introduce you. Yeah. So welcome everyone to the quick seminar. Our speaker today is James Daniel Whitfield from Dartmouth College. So he's done a lot of interesting work on using the theory of quantum computation to understand the hardness of problems in quantum chemistry. And today he's going to talk about limitations of Hartree-Fock using quantum resources. Thanks very much, James.
Yeah. Hi, everyone. Hi. I'm very excited to be here. I'm originally from Maryland, from Laurel, PG County. So it's almost like being home virtually. Anyways, today's talk is about the limitations of Hartree-Fock using quantum resources. I think in many ways, before the talk started, you guys was telling me there's a lot of graduate students on the line. But I think a lot of the conclusions that I'm drawing out of this inside this work that's in the archive reference given, that's done with Sahil Gulania at USC. A lot of the conclusions there are, I wouldn't say obvious, but they are conclusions that you could have drawn back in the 90s, right? From a lot of the theory that we already have, especially with Hartree-Fock, considering things that we already know about Hartree-Fock and things we know about quantum resources. And what I'll try to do is give a recap, a summary, and the motivation for why we're looking at these limitations of Hartree-Fock and where we think quantum resources might be used, right? The entire inspiration for this paper, well, there's a couple of inspirations for the paper. Me personally, I've been thinking about Hartree-Fock for many years. And I have thought about Hartree-Fock on a quantum computer for also many years. And I thought, well, I tried a couple things and they never really worked. And there was a recent paper by Google that came out just, I guess, a month ago or so, applying Hartree-Fock on a quantum computer. So I was super excited to see that there was an effort to apply quantum computation to a quantum computer. However, the unfortunate thing is that, there should be no speed up, right? And so I was actually looking at that paper, hoping there'd be some speed up, but I don't think that you should expect any speed up using Hartree-Fock on quantum computers. And I'll give some ideas there, as well as some connections to other ideas inside of complexity theory, and try and give a nice overview of how electronic structure actually appears inside of quantum chemistry, and hopefully give you some motivation as to what's going on here. Okay. Okay. So what the crux of the paper says is like a Twitterized version of the abstract. The application of quantum technology, Hartree-Fock, in their paper was a hardware benchmark, which is fine. As a hardware benchmark, they actually introduced new circuits and things like that actually won't discuss. But the important thing that I want to draw as a conclusion is that it's unlikely to have a dramatic impact on the practical approaches to Hartree-Fock. And what you see on the right-hand side is really the main technical contribution of the paper, and it hopefully opens up new doors in understanding when Hartree-Fock and electronic structure problems in general are hard or easy. And what you see here is actually a potential energy, not a potential energy surface, but rather a Hartree-Fock energy surface. And I'll introduce this again later, but what you can see here is this Theta 1 and Theta 2. You see nice periodicity inside of different directions. There's actually really nice things you can say about this in some small results that we have about the analytic nature of this. And we're thinking a bit about how permutations appear inside of the space versus rotations. And so a lot of things that are going to come out of this, hopefully. And what I hope to get across by the end of the talk is what this picture represents. In order to do that, what I want to do is first give an overview of our research and of electronic structure, of quantum computation, and the intersection thereof. Then I want to talk about optimization. This will allow us to discuss computational complexity. And then for the last part of the talk, we're really focused and dive into the Hartree-Fock theory. Okay. So from my point of view, the motivation for quantum computing is that there's many quantum systems in chemistry and physics that are of interest to us. I think one of the most interesting aspects of quantum computation is thinking about when we do and don't need it. And that will really be the crux of this, of a lot of the things that we'll talk about today, is when we do and don't need quantum computers. So if we look here at the classical side, we have proteins, cells, and viruses. These are all very large objects that you're normally going to treat with mainly classical mechanics. There'll be some quantum information or some information from the quantum domain that's fed in order to parameterize these classical simulations. How much is the force between two atoms, or how much is the torsional angle between some particular configuration, and that will be informed by quantum mechanics. And so that's what you see when we talk about solids and liquids. we have classical models for these systems that are informed by quantum mechanics. Now, if we go to molecules, which are smaller, then you have molecules, you care pretty much, you need to use quantum mechanics from the beginning to the end in order to talk about molecular energies at the energy scale. And then as we go up in energy, we talk about atoms, we talk about relativistic effects, you have spin orbital coupling, nuclei, you have to use relativistic effects, fundamental particles, you start using quantum electrodynamics and field theory, and you start to go into the high energy regime. And there, quantum's required, plus all the other aspects of physics that you may be able to round out. And as you go up inside, as you go up in approximation, you'd expect the Bohr correspondence principle to enter in somewhere into the classical simulation sufficient. And so one of the questions that I really have is, where do we draw this line between these 2 points, right? Is there a sensible way to do it? And that leads us to this idea of the border technologies, the famous paper by Wilczek-Zurek in Physics Today. And he's talking about the difference between classical and quantum domain. But he talks about the classical and quantum domain in terms of measurement, in terms of how you treat operators, how you treat quantum fluids versus atoms, electrons, planets, us, things like this that kind of talk about the difference between quantum and classical. My group's research interest and the question that we're really pursuing is, what is this boundary not as a conceptual boundary, but what is this boundary as a computational boundary? Right? So how do we actually find problems that are appropriate for the quantum domain, and it can't be done in the classical domain? There's a quantum supremacy experiment, which I'll talk about a bit later. But this is really what we're trying to think through. This is my research group. We're actually missing a few members here. This is from before COVID, obviously. We're all very close together in this picture. So we have a postdoc, James Brown, recent postdoc, recently graduated PhD student, Kanav Satia, Riley Chin, and Weishi Wang, and Jun Yang. And then we have undergraduates, Ben, Kat, and Omar. And we're working on a variety of projects, and one of them is about hybrid quantum classical algorithms and time-dependent density functional theory, quantum simulation for fermions. How do we actually encode the antisymmetric subspace in order to do simulations on a quantum computer? And then today's talk, we're focused on why are we even doing any of this? Why build a quantum computer? And hopefully I'll give some reasons to and reasons not to. Right? Okay. So this is supposed to appear second. Any case, this effort on spin to fermion transforms is really about structure of fermions and coding the fermions into spins. So we have fermionic algebra. We'll go over this in much more detail. Hopefully it'll make much more sense, but the idea is we have some algebra of operators that describe electrons. We have some algebra of operators that describe spin systems. And we want to map these two algebras in order to get one to work well in the other. We've done a whole variety of methods going back to 2016 and perhaps even earlier, thinking about Jordan Wigner, Bravik-Katev, different ways of encoding into Fenwick trees and lots of other things. One result that we have that should appear by the end of the week is thinking about how do we derive this Bravik-Katev super fast encoding, which I'm not going to get into at all. But the idea is that we go through this idea of gauge fields and fermionic modes, and then we want to go to gauge fields. So this gives another way of thinking about how to make local simulations of fermions using something very closely connected to Tor codes. And yeah, that would be a whole separate talk. Another whole separate talk that would be interesting to get into, but won't be for today. And this shouldn't be covering this, but there's a movie here. It's yeah. In any case, we look at time-dependent density functional theory. I will explain density functional theory later on in the talk, but this is an area of research that's mainly run by James Brown and Jun Yang, whose pictures should also be on the slide. This is James Brown, Jun Yang. In any case, these aren't the topics for today. I mean, what we have here is the quantum classical algorithm. Yeah. Oh, this is not one point, so we'll just skip over that. But in the time-dependent density functional theory, one of the main reasons that our group focused on the time-dependent density functional theory is that the time-dependent formulation of density functional theory, we expect that we may be able to get some speed up. So this is where we think of the difference between doing time-dependent density functional theory. We're trying to propagate dynamics. You're given some initial wave function and some Hamiltonian, and you want to apply the propagator of this Hamiltonian. There should be a psi I here. Yes, or the other option is that you want to minimize over all possible wave functions psi, the expectation value of some Hamiltonian to find the ground state. You want to find some optimization procedure to find what is lowest state here. This optimization procedure is actually what gives rise to many of the worst case problems that we can argue. The dynamics problem, however, is essentially what a quantum computer does. When you think of a quantum computation, it is applying gates inside of some prescribed sequence and then measuring some output. Here, we're applying gates inside of some prescribed sequence to build this unitary propagator. We would apply it to psi I if we've written the equation correctly, and you get out psi t at some later time. These Hamiltonians can be of many different forms. I'll discuss the Hamiltonian forms in much more detail subsequently, but for some simple examples, you have your very physical Hamiltonian here is a kinetic energy, p squared over 2m. You have the potential energy for the one body potential energy, and you have the two body potential energy, and there could be other terms. The same idea applies for spin systems. We have here a second order spin system where basically we have two spins being coupled. You could have k local where you have k spins being coupled, and so on and so forth. These are just different Hamiltonians. We can think about evolving under these Hamiltonians or finding the ground state of these Hamiltonians. And there's a very big difference conceptually and in spirit between these two efforts. Okay, so it's important that if you're thinking of applications of quantum computers, you want to focus more on the dynamic side rather than the minimization side. And I'll really try and underline this point as we go through the talk. Okay, so it's just an overview of what we're going to discuss today. I'm thinking about how do we apply these things at the quantum scale. Well, we need to use quantum mechanics. We're not going to go to enough precision that we need to use relativistic quantum mechanics. And in fact, we'll ignore spin for the most part during this talk. But in order to kind of highlight some of these ideas, what I want to start with is just a brief summary of computational complexity as a brief reminder for those of you who have or haven't seen it. So the way I like to think of complexity classes in terms of P and NP and these deterministic, non-deterministic classes is you can think inside these deterministic classes, P, which is P for polynomial time. This is bounded error probabilistic polynomial time, quantum bounded error, quantum polynomial time. And then there's corresponding classes that where where if you had a hint, you could solve it very easily. Right, so that's the idea of all of these non-deterministic classes. Too fast there. Yeah. So the way I like to think of this inside of a high level, if you haven't seen it before, the way you should think of this is that on the left-hand side, you have some expert, which is normally a wizard, so Merlin or whatever unbounded computational power that may be interacting with, and they can give you the solution. They can give you a hint that will allow you to solve the solution, right? So if you're a student, say an undergraduate, and you ask, hey, how does field theory work, right? Well, it's going to be they can only give you back certain answers that you'll understand, right? But if you're a graduate student, so you have your Master's of Arts, okay, it's not what MA stands for. MA stands for Merlin Author. But if you have a Master's of Arts and you're a more sophisticated student with more resources, then I can give you a smaller hint. I may just give you a textbook. And if you're a very intelligent student or a very good researcher or whatever, if I want to explain you something, maybe I just give you a very small hint and then you go think about it for a couple of days and you come back and have the full theory worked out. And so that's the idea, is that these different verifiers have different amounts of power, and that means they can get different types of hints. In the quantum Merlin Author, the student should be able to take in a quantum hint. In Merlin Author, the student should be able to take in a probabilistic hint, or at least solve the problem with use of probability. In a deterministic case, it needs a deterministic hint that will then allow you to solve the problem in a polynomial amount of time. So it's very much like a textbook. Someone gives you a textbook, it's not going to take you the same amount of time it took for them to write the textbook for you to read the textbook, no matter how complicated it is. Well, maybe that's not true, but if they did a good job of writing the book, it should be much easier to digest the book than it is to reproduce it on your own. And that's a very easy way of thinking of these non-deterministic classes versus deterministic classes. Okay. So for a concrete example, phone books, if you guys still remember what these are from whatever that may have been, well before COVID. So in any case, if there's a phone book, so some random phone book, and you're given a name, It says, what's Alan Turing's number? Well, you need to look up his name. You need to find his name. It's very easy. You go to the A section, and then you go to the T section, the TUR, find his name, report the number. However, if you just give me the phone number, 240-520-7847-202, see, DC, then it can be a very difficult task to go through the entire phone book to find out who has that phone number. Okay, and this is a picture of Alan Turing from the movie Imitation Game. Now, in this example that I said with Merlin author and these different MP versus P, you have some unbounded, super powerful Merlin magician who can just solve the problem, somehow go through the phone book, knows the entire phone book front and backwards, and he can give a hint. And so over here is a statue of Arthur, King Arthur. And so Merlin would give King Arthur a hint, right? So this is L.A. Whitfield. So if the task for King Arthur is to find out who has phone number 202 XYZ, then if you're given the hint L.A. Whitfield, well, you know to start inside the W section, right? You know to start inside the WHIT-FILD section, and there may be 4 or 5 different Whitfields, but now you've narrowed down your search space tremendously, and you're able to find it with this rather strong hint, okay? And you find out that it's, I don't know, Lily Azul Whitfield or whatever. Okay, so that's a very basic introduction to computational complexity, I think. Yeah, these things are a little bit out of order, so I will start here. So we have the electronic structure problem. The electronic structure problem is that we're given some Hamiltonian and some external potential, which defines the instance. There's a number of electrons. There's some energy cutoff, or some energy cutoff that we want to know is the energy above or below this cutoff, and some error parameter delta, right? In order to formally define this as NP, QMA, or any other complexity class, we need to specify what delta is, you know, in terms of the problem size, and all these things are all very important to do correctly. But at the highest level, the input to this problem is the external potential, the number of electrons, the energy of question, and the precision at which you're interrogating the question. So E0 is a ground state for this Hamiltonian. You're supposed to find a ground state and then see if the energy is above or below this cutoff energy with some fudge factor there. Okay. Right. So here in this case, what the output would be is either the energy is above this energy cutoff plus delta, or below this energy cutoff minus delta. This delta is just a way of saying that you don't need infinite precision, right? So if I ask you, is it exactly above 0 or exactly below 0, it may be very difficult if it's 0.000001, right? Yeah. The other important thing about doing the electronic structure Hamiltonian, electronic structure problem, is that if you note this Hamiltonian has T of X, W of X and Y, and V of X, and principal is X is a coordinate of all the electron coordinates. Again, I mentioned that I'm not going to explicitly discuss spin. However, if you want to discuss spin, it's not very hard to add in here. But in the results that we have inside this paper, we just used closed shell. So that means effectively spin's always 0, which means that you can simplify a lot of equations. But yeah. If you have any questions or any particular interest in the spin sector, please just ask them, and I'll address them one at a time. In any case, what we have here is that to go to the antisymmetric subspace, this Hamiltonian is in all the subspaces, the bosonic, fermionic, and then all the mixed symmetries in between. But if we want the completely antisymmetric subspace, we can use operators that satisfy this algebra. This is the algebra that I introduced very early on when I talked about our spin to fermion mappings. All right, each one of these operators, the A sub j, the j is an index that will label the different orbitals. Each one of these orbitals is a single particle function. So a single particle function means that it is only for one electron, one particle. So it's going to map these R3 to some real number. Again, we're going to make some simplifying assumptions. In principle, this could be complex, but we're just going to assume it's real. We don't have any magnetic fields. We're not going to think about those for today's discussion. Then we could also write down inside this antisymmetric subspace a rank R state. And by rank R, what I mean rank is that you're only adding up are different Fock vectors. Right? So these Fock vectors are just combinations of products of these creation operators. So you create operators and you decide which ones will be occupied or unoccupied. If it's 0, then it's not occupied. If it's a 1, then you're creating a 1 dagger to the 1 power. And so that'll appear. You multiply these out and it occupies these states inside the vacuum state. And you sum over some coefficients. And pay attention, this rank will be important. This will help simplify some of the discussions that we have later.
Hi, James.
Yes.
Actually, is this a good time to pause for questions? Or,
Sure.
Yeah, no. So if people want, they can type questions into the chat window, but actually we're a pretty small group, so we might also be able to take some questions just live.
Yeah, the questions are fine live, or I'll elaborate on these points next. So hopefully it won't be too hard to.
Okay. Okay. Yeah, and if there are no questions, then feel free to go ahead.
Okay. So a few things that are additional considerations. So we just mentioned this projection of the antisymmetric subspace of H. We mentioned this finite basis that we have. We're going to choose some bases. We're going to have M elements. This will be important later. We're going to ignore electron spin for the most part. We're ignoring relativistic interactions. We'll discuss magnetic interactions briefly. The electron nuclear coupling, we're going to assume the nuclei are only incorporated into electronic problem through this external potential. And I'll elaborate on that a bit more in a second. The precision required for quantum chemistry, for chemistry in general, if we're thinking about what's happening at room temperature, do we want to have precision that allows us to know what processes are or aren't allowed at room temperature? So for instance, you can imagine that there's 2 conformations of a molecule and you want to know which one is preferred or what the preferences are between the 2 of them, then you're really going to have to use the Boltzmann distribution, which will then cause you to need relatively high precision in order to actually classify these states. So that's why our precision level is about thermal energy. Another important point that I think sometimes gets lost, and I didn't write it down explicitly, but we're interested in the electronic structure problem. We're interested in the ground state of the electronic structure problem because the ground state's the only state that's appreciably occupied. The typical gap for molecules between the ground and first excited state is relatively large. In fact, inside the visible region, so you can actually see it, right? It's fantastic. We can see a lot of things around us. And these are quite often due to electronic properties. Consequently, what that means is that almost everything you see around you is inside of its ground state at room temperature, right? Of course, you could excite it and you can have excitation, things like this that'll happen due to photons and things, interactions. But typically, our molecules would be insulators that we discussed inside quantum chemistry. Okay. Now, there's also a number of variants of this problem. So if you note here, this is just T with inside of real space, W inside of real space, some interactions with 2 multiple particles, and V inside, also inside of real space. Now, I already mentioned this idea of projection to a finite basis. And so we can, oops, too fast there. So if we have this electronic structure problem, as it's stated previously, we just had an external potential. We had no structure to the external potential, and we can start installing structure into this electronic structure problem piece by piece, and this will actually cause us to be able to classify or not be able to classify, or get closer to the physical problem or get further away from the physical problem in different ways. Okay. So the simplest case, the simplest one that's the most obvious extension of what we just discussed. Before we just said they had some external potential. Now, if we said external potential is only generated by nuclei, then that's a further restriction, right? You can imagine you had an electric field inside the background that's generating some, electric field, external electric field. But in this case, we say if we only have nuclear fields and we're just talking about molecules and atoms and systems of that sort. Then we can go another step further and we go to electronic structure on a finite basis. So now we projected each one of these operators that were in real space. So V of R, now we've integrated to make them into some finite basis, and now we're left with some coefficients in front of this Hamiltonian. The coefficient tensors here is something that we are interested in studying in our research group to kind of understand when these are or aren't allowed, but that will be something that we'll discuss at another point. The reason why that is interesting is that these problems in red are known to be difficult, right? So if we take electronic structure with generic coefficients, meaning that we can allow anything for HIJKL, anything for HIJ, meaning that it didn't have to come from any intervals of this sort, then we can show that this is QMA hard. Similarly, for the electronic structure problem with local magnetic fields, so each one of these sigma i's, SIs would couple to the spin, which I didn't discuss at all, but nonetheless, it would couple into the spin, and you can have your problem encoded into the spin states. And this was a famous paper by Norbert Schuh and Frank Verstraete, showing this is QMA hard. You can embed two local spin Hamiltonian into an electronic structure problem with generic coefficients, but it's not clear if these coefficients came from an actual basis set, an actual set of interactions, an actual external potential. So that's a question that I think is rather interesting, but still remains open, at least from my point of view. Maybe some paper from the 50s or 60s, someone thought of this, but. Okay. All right, so now it's actually a very good time to just pause for questions to ask here. If there's any questions about what we set up. So the part in blue is what we're going to be using for our problem statement for the rest of the talk. We'll have some finite basis, and we'll only deal with the integrals Hij, Hij-KL, and we'll assume they came from an actual basis with actual integrals generated by doing some integration over the kernels. Okay.
So this is a minor question, but I'm just curious. So when you make this into a computational problem, how would you encode the coefficients? So I guess they're real numbers. Is there a particular way of encoding them and describing their length?
So you mean how they're actually stored?
Yeah. So like, yeah, when you, how they would be stored and how that would affect, how you interpret the complexity.
Yeah, sure. That's a reasonable question. So let me say that the complexity in terms of like the discretization would be that this is some basis set that ranges from J equals 1 to M. And so quite often when you hear people quoting the complexity of a computational algorithm, it also quoted in terms of the number of electrons and the number of orbitals, right? So then you have this scaling with M. So how big is your finite basis will dictate parts of your algorithm, which we'll see exactly where that comes in. But other than that, what actually happens is that these orbitals, so phi j, phi I, is chosen to make these integrals easy. Right? So choosing the orbitals to make the integrals easy is great because then we can do all these integrals very quickly. It might be m to the 4 integrals, but one of the things that happens when you're doing very large scale electronic structure calculations is that you can compute these on the fly, right? So if you're getting ready to compute matrix element whatever, you can compute that integral as needed, or compute a batch of them as needed, and then you can. There's a lot of very clever techniques. People have been thinking of doing electronic structure on computers since before they were computers. We're going to talk about Hartree-Fock theory, and Hartree-Fock, his father was a retired engineer, and his father did the first Hartree-Fock calculations by pencil and paper. So people have thought a long time about how to organize these integral coefficients and how to actually set them up, what to use for them, how to make them easy to compute. Okay. Does that help?
Yeah, thanks.
Happy to. All right, so so let me go from here, which is the problem statement. Basically, we have this. We're going to discretize this, and we're going to compute it inside this finite basis. We have 1 to m basis functions. Now, what I want to kind of underline here is that this VQE implementation, so this is variational quantum eigensolver. There's a lot of different things that have a very similar flavor. This quantum approximate optimization algorithm, this unitary couple cluster, adiabatic quantum computation, all these are quantum optimization techniques. Doing optimization on a quantum computer is a very hard task, right? So optimization in general is non-deterministic polynomial time hard as a task. And the state preparation, however, belongs to this quantum Merlin author complexity class, QMA. So this variational quantum eigensolver is applying an NP-hard heuristic to a QMA hard problem. So saying that there's no theoretical reason why this should work. Right? It's not saying that it doesn't work. Right? It can very well work. Hartree-Fock works very well classically, but there's no assumption that it should work better for a quantum problem. Okay. This QCMA, which is quantum classical Merlin author, is the same idea of this Merlin author game, except now you're a local Hamiltonian problem. So it's a Hamiltonian that we had before, but now we're going to be promised that the ground state of the Hamiltonian has an efficient classical circuit to generate it. This is a natural way of describing VQE's problem, right? So this would be a more natural class of applying an NP-hard heuristic to a QMA hard problem, because we're saying the promise is that this QMA hard problem at least has a classical solution. And then you still need to find it through this VQE algorithm, but at least you know that there's some answer that you can find. And so I think this is an interesting complexity class. I found out about it 2 weeks ago from Bill Pfefferman, who has written a few papers on it. I don't know so much about it, but it seems like a very interesting direction to head in, especially given some of the things that are happening inside of the quantum literature. So yeah. Okay, here's a whole table full of different approximations. The only ones that are of interest for us for this talk, in the interest of time, I will skip over them, the rest of them, which you can have a second to read. The Hartree-Fock method, which is what this talk is about, is to self-consistently solve the one electron problem with mean field generated by all the electrons. Great. Density functional theory reproduces the density of which all property systems are functionals. The nice thing is that Hartree-Fock and density functional theory, these two methods at a computational level are the same, right? At a theoretical level, they're very different, but at a computational level, the techniques that you use for Hartree-Fock are also techniques that you use for density functional theory in practice, okay? This is the self-consistent field method. Okay. All right, so there's a conjecture that I have, and I don't know if we can prove the statement, if there's easy way to construct counterexamples, or how to even identify instances that might be a counterexample. But we could think that for every instance of electronic structure optimization problem, if there's a BQP time algorithm that solves it, perhaps there's also a p-time algorithm to solve the same instance, right? This would be to say that if you can find the ground state of a Hamiltonian using VQE, then perhaps you can find the ground state of the Hamiltonian using a classical method altogether, right? That argument is rather difficult to make. I don't know that you can, but I wouldn't be surprised if this is true. And I think a lot of people might not be surprised. Some people might be, and some people might not be. I think from a technological business side of quantum computation, this would be a very negative result, but it doesn't invalidate quantum computation. So if you note, the quantum supremacy experiment uses a BQP problem rather than QMA hard approximation problem. So it's not finding ground states, it's rather doing the propagation. And this is the major difference between dynamics and optimization. Okay, so this brings us to the last part of our talk. This is a good time to stop for questions. Okay. If not, then let's dive right in. So Hartree-Fock I really like as a problem. This is one of the first algorithms that I learned inside electronic structure method, and I just found it fascinating that someone could write it down, and just the history of it, history of science. This goes back before computers around, and it has a very deep connection to many Nobel Prizes. The entire idea of frontier orbital analysis has won Nobel Prizes in chemistry, and this is all based around this idea of orbitals which are coming from Hartree-Fock or density functional theory. And I put them together because they're all around the self-consistent field method. The output of both of these methods, the output of self-consistent field methods are orbitals. These orbitals are giving me pictures of where the electrons at, how the electron densities around the molecule, where do we expect the charges to be, where the nodes inside the wave function are, a lot of things that come out of just this orbital analysis. This is not the in-body wave function. Remember, each one of these orbitals, the orbitals that I've drawn here, are one particle functions, right? The fact that the one particle functions means that this does not describe the full system. Yes. So I'll explain how we get this functional in a moment, but first let me give the high level picture, the intuition behind this self-consistent field method, right? So I like a very nice story of the self-consistent field method where you imagine you have a violin and you have a bunch of violinists and a bunch of musicians, in fact, and each one of these musicians are in their own separate booths. In their separate booth, they have their instruments, and they're all trying to tune the orchestra. So you normally go to orchestra, you hear everyone at the beginning of the orchestra or the beginning of the concert, you hear all of them, everyone playing all the notes at once and trying to tune. Now, if you want a non-interacting system, right, you don't want them to hear each other. So what we do is put each one inside their own separate booth, and that's effectively making an orbital for each one of them. In that orbital, they play their note, and that's effectively a field, right? So you can think of a field, the energy somehow connected to frequency. This is a sketchy explanation, but I think an apt one nonetheless. So in their booth, they play their note, whatever whatever note A it is, then that gets recorded. All the notes A from all the different booths is then averaged, and then that's played inside of each one of the booths individually. And once you hear it, you say, oh, I was off, so you tune up, right? And then you play your note, and it goes back, there's an averaging procedure, and that note gets played back in your booth. You say, oh no, I overtuned. So you tune back down. And then you keep going procedure after procedure. If everyone's tuning carefully, then what'll happen is that it'll converge to some A note that's averaged and everyone's playing the same A note. Okay, you might get the wrong A note, but you still have converged and everyone's at least playing something that's in tune. And that's the idea of self-consistency, that everyone's playing a note that's consistent with all the other notes. Okay, this is a sketchy picture of it, and we'll go through the full derivation of how we get this. This GSCF is the mean field. V and T are the operators we've already discussed. This N is the density, and this PMN is just discretizing it into the basis that we discussed as before. And we'll derive this functional a bit in a bit. Skip this. Right. So the Hartree-Fock optimization procedure, the problem that I just described to you, and the method that I just described to you of this SCF is a bit different than just backing up and saying, what are you trying to do in the first place? What you're trying to do in the first place is find the minimum over all rank 1 Slater determinants. So remember, for its higher rank, it would be some of these different Fock vectors, these different Fock strings here. But this is just a single Fock string with some operators B instead of operators A. So note that A is some basis, whatever, some basis of operators. We make some linear combination of these A operators through some unitary matrix. This is again assuming that everything's in an orthogonal space. When we do quantum chemistry with something that makes the integrals nice, it also makes the basis set non-orthogonal, which leads to a whole bunch of details. In any case, what you want to do is find the expectation value of this Hamiltonian, whatever Hamiltonian you have, with respect to these rank 1 density matrices, rank 1 Fock matrices. So what you can do to actually bully this equation and arrive back at the expression that we had previously is just take this Wij and evaluate what the expectation value of Hij, Ai, Aj in the B basis, right? So you have B and you have the B's acting on the left and the B's acting on the right, and then you bully everything through and you end up with this PQ. So you get a W coming from the left, the W coming from the right, want to be conjugated, so you kind of have some intuition there, and then these will show up everywhere. You only have N of the electrons occupied, right? So this is from 1 to N, and there's M total, so this is some projector onto N states. And this P is the charge density matrix that we just described in the previous slide here. It's the same P here. Okay. So this is the Hartree-Fock formulation 1 as an optimization problem. We bully it a bit more. We can plug in this P and we end up with some expressions here. So this is the integrals, this is anti-symmetric integrals, but then you have P quadratic. You can pull it out and you end up with the Coulomb operator and the exchange operator that is just literally the sum over R and S, and then you put it to J, and the sum over R and S, the minus sign, put it to K. And this is called the exchange because if this was P and R, that would be the exact Coulomb integral, just the Coulomb charge distribution of two things. The exchange is that you exchange two of the orbitals. That's super important. So let me stop here. And this is just the connection between density functional theory and Hartree-Fock. This should be a minus sign, but you can ignore that for the moment. The idea of Hartree-Fock versus density functional theory is you just change this GSCF. So this G self-consistent field method, you just change it to whatever you need it to be. Inside of density functional theory, you actually are allowed to pick this quite arbitrarily. So this exact exchange from Hartree-Fock, you can imagine that you just change that as whatever you want it to be, and then you're talking about density functional theories in the first place, right? Each one of these is a functional of P, which is really just a charge density matrix discretized. So that's the density functional theory. So we have this expression just from plugging in our W's. And then we end up with the Hartree-Fock functional, right? So now we have E of P. Plug in this P, and we're taking the trace of P with the one-body terms and with this GSCF, which also depends on P, making it nonlinear. Right? This is the whole nonlinear optimization of Hartree-Fock. And then what we have here, and this is important, and this gets almost back to the very beginning of the talk, is a way of characterizing these charge density matrices that avoids some redundancy, but effectively gives us the parameterization of the entire space, which is really nice, because then we can just parameterize and actually see all the density matrices starting from a single point. We have some P, and we have some X, and we can look at the entire space. And so then the optimization problem becomes an optimization over all possible values of P, which in turn is an optimization over all possible rotations that we can make. To actually parameterize our space, in the beginning, we had this theta 1 and theta 2. These thetas are just the parameters that go into this X that tell us how much we're rotating from this initial charge density matrix. Yes, so we make X block a skew symmetric, yes, skew symmetric. So now if you take X transpose, and then you get minus X, which is great because then we take the exponential. This gives us an orthogonal matrix, which would then allow us to just rotate this object nicely. And the same thing's said here in the bottom. Okay, now this is a good time to pause for questions. Also, if this makes sense, then we'll leave it. Okay. All right then. Moving on. Oops, not so far on. So again, I mentioned that the motivation for this paper that we wrote about the limitations of Hartree-Fock was because there was a paper by the Google AI Quantum Lab and many of their collaborators, a very nice paper that discusses Hartree-Fock on superconducting qubits, on a superconducting qubit quantum computer. When I first heard about the result, just verbally heard about it, I was super excited, as I mentioned. But when you really go through the details of the paper and you actually read it, the paper actually has nothing about computational complexity. It mentions nothing of the fact that this doesn't offer any speed up. This is a way that you might be able to get a speed up if you're dealing with super large charge density matrices, that the evaluation might be faster on a quantum computer. But I don't think that's really a realistic application area for quantum computing. The other way that quantum computers could help for doing Hartree-Fock is if you wanted the exact solution. So in the case that I want to search over all possible charge density matrices, and I really, really want to look over the whole space, then if I'm using brute force, then I'll get a quadratic speedup using Grover search. This paper introduces new error mitigation techniques, a decomposition for the circuits, and they use this algorithm for Hartree-Fock for this basically rotation of the charge density matrices. You have this functional as a function of parameters, and that just gives you some VQE functional. And this is just used to benchmark the quantum device. So I want to make sure they could do something on a quantum computer at all. But it does not actually give a speed up. But the paper doesn't mention that, which is why we thought it was a reasonable time to write this. Don't need this at all. So what I do want to say is that Hartree-Fock itself is NP complete. This is in the appendix of Schut and Verstraete's paper from 2009. I will mention that the Hamiltonian that they use there is a Hamiltonian with generic coefficients. So it's not necessarily derived from an actual molecular system. Okay, so in polynomial time to evaluate the functional for density P, it's efficient. And then it's not necessarily efficient to find the minimum of this functional. So it's pretty easy proof as far as things go. To actually complete the proof, to actually show that in the ground state of this problem, you can embed other NP hard problems, and you can do it by just modifying the coefficients of the Hamiltonian appropriately. Okay, so with the last 12 minutes or so, I just want to give a little bit of what we do. It's spelled wrong. Please forgive my typo here. But I want to give a little sense of what we did do inside of our paper to kind of illustrate the fact that this shouldn't converge for all instances. And what we did is just took simplest examples we could to show illustrations of non-convergence. And then we actually made really nice plots out of them. And the fact that we have these very nice plots means that we can start looking at when does the problem become hard, when does the problem become easy, when are you close to minimum, when does your initial guess match what you expect, and things like that. So we can see some very nice things. This is a RHH is the distance between hydrogen. So this is molecular hydrogen, so H2. And this is internuclear distance. And this is just the parameterization of the rotation. For the minimal basis for hydrogen, it turns out it's only one parameter space. So we get a very nice picture of it. Yes. Very nice picture. The same thing as the last image, but just animated because it looks cooler. I don't know. It's also nice to note here that if you look, the number of critical points here is not the same as at small values for R. Right? The fact that the number of critical points changes along this Hamiltonian path also indicates that you can't use Hartree-Fock functional for excited states. There's very nice characterizations of how to generate approximations for excited states using something very close to Hartree-Fock theory, but this illustrates you can't just directly use the ground state functional to do excited states. All right, we found a couple of different examples where convergence fails. So the interesting thing is that going through the code and looking at how the Google optimization problem actually works, we looked at just some very simple examples, and we just tried perturbing the initial state. So you start from some initial state, which is whatever it may be. So actually, the way the Google experiment actually went was that you found the ground state, the actual Hartree-Fock state, and then perturbed it by some value lambda. And in the open fermion paper, it's a very small perturbation of 0.1. We used an order of magnitude larger, and in some cases we used just a factor of 7 larger. But you can see that if you move further away from your initial state, not a very big difference will cause you to either converge to the ground state or converge to an excited state. Same thing happens for H3+. H3+ is a fantastic example. H3+ I'll illustrate in a second, but it's a fantastic example because you have three orbitals and 2 electrons, which means that your space is parameterized by just 2 parameters. It's fantastic. So we get the plots at the beginning of the talk. So we can really see what happens for all 3 orbital 2 electron problems and plot them quite nicely. This is our original plot that I showed at the beginning of the talk. We have theta 1 and theta 2 controlling the rotation of the occupied orbital to the first unoccupied orbital, and the rotation of the second the occupied orbital to the second unoccupied orbital. And this gives you a way to reach all the different states. Obviously, we go, this is a value for theta, so it's e to the minus I theta times the generator. So obviously, if you go far enough, you're going to repeat. And that's what you see inside this image. And so we look at effectively the first weird Brion zone. I don't know exactly how to describe these things yet. I'm thinking a bit more than mathematics. But what we have here is just different minima that you see inside of this optimization space. One of the other things that we're quite interested in is thinking about the difference between permuting the orbitals and rotating the orbitals. Right? So you can permute the orbitals, you just have some set of orbitals that are defined by some rotation from initial state, but then you can permute on top of that. And so it'll be interesting to kind of see how these points are related when you think of the same problem in different settings. This P core is the charge density matrix that corresponds to ignoring the 2-body Hamiltonian. It's a very common initial guess for Hartree-Fock, that quite often people start Hartree-Fock from just ignoring the 2-body interaction altogether, computing what the charge density matrix is for the core Hamiltonian, and then including the self-consistent field second. There's other guesses you can choose for the core for the initial charge density matrix that you can rotate from. And yeah, so yeah, we have a little bit of time left, so I will stop here. Not stop here, but rather just discuss a few things. So examples that we chose here to illustrate the fact that it's hard to get this to converge were relatively simple, right? We took H3+. This is just 3 hydrogens, and we actually had a linear H3+. It's not a physical system, and that's not the point. The point was to see whether or not we can make problems that are difficult, right? And can we make problems that are difficult and show that they're and show which optimization procedures work the best, what formulations of optimization procedures work the best? Can we convert from one optimization problem to another? These sort of questions that we have about Hartree-Fock as a computational algorithm, and then computational algorithms in general with respect to quantum computation. So our future work, we want to use these toy systems and their Hartree-Fock energy surfaces to characterize and classify the landscapes, right? So if we think of this landscape for different values of the internucleus distance, so this is at 2.5, if these are far enough apart, they don't interact and all the states have the exact same value. So you can ask how many minima there are, how the critical points change. So if we even look at the video, you can see that this is a much more complicated surface, many more minima that gets trapped in. You can see that the minima here are very close together as you get further away from the equilibrium distance. But here it's very easy to find. You should go to this point relatively quickly, start here and you go down steepest descent. Here you have a chance you can trap in some local minima. And because we have this very simple visualizable ways of seeing the surface, what we want to do is actually see if we can actually make enough surfaces, control the parameters, take the generic version of the Hamiltonian, and just pick random integral tensors, take integral tensors from random physical systems, and see which of these problems generate hard instances. Which of these problems you can solve with a VQE ansatz better than you could with just the self-consistent field method. This is the first step towards understanding the computational boundary between quantum and classical. What we really like to do is understand this numerically, and then go back and return to it with statistical mechanics and a lot of the techniques that people have applied to NP hard problems. In particular, 3-SAT, there's a lot of theory done there in terms of looking at how 3-SAT actually plays out for in terms of when the problems are easy or hard, which I think is very fascinating analysis. But can we make something that's more physical to figure out, is there a control parameter for how difficult an instance of Hartree-Fock is or isn't? To really answer this hypothesis that I posed earlier in the lecture about whether or not we would expect for every classical problem, for every quantum problem every quantum optimization problem we can solve, is our classical optimization solver that can do the same, in roughly about the same amount of time. Yeah, so that's the compelling question. Do we expect quantum computers to perform ground state optimization better than conventional methods? Not convinced. I'm not sure. I think there's a lot of other applications of quantum computing, particularly this time-dependent density functional theory, as well as many other optimization, many other problems inside of BQP. Okay, so I have 5 or 6 minutes left for questions if there are any, and I will also plug. If any of you guys are teaching quantum computing, please check out QBraid. Let us know if you want to use it for your class. Explore quantum computing. If you're an undergraduate and you've never seen this before, QBraid's also a nice place to go. We're funded by the National Science Foundation and the Department of Energy, and we're part of the Quantum Information Sciences at Dartmouth with several other quantum scientists there, Experimentalists, a much smaller version of JQI. No? So.
Thanks very much.
Yeah, of course.
Yeah, so we have time for some questions.
So I have a quick question, but might be more of a comment. And I think you pointed this out nicely, the difference between sort of optimization and dynamics. And that the quantum supremacy problem seems to really fall in the dynamics range rather right now than optimization, which we still don't know whether we can really get something that is a speed up. Is that what you're driving at there?
Yeah, that's exactly what I'm saying. I think a lot of people who've done quantum computing long enough know this, but there's a lot of people entering into the field, especially coming from chemistry, that might not recognize that difference. But yeah, that's exactly what the paper is. From a real quantum computer.
I have a comment, maybe also a question to go along with it. There's a very famous paper by Elliott Lieb in 1989 on the Hubbard model. I don't know if you're familiar with that paper or not.
I'm not sure which one, but Elliott Lieb has a lot of very good papers. So.
Well, it's called Two Theorems on the Hubbard Model. It's a paper where he proves that the attractive Hubbard model always has a spin singlet ground state, and the repulsive Hubbard model at half filling on a bipartite lattice that has a different number of electrons, different number of sites on each sublattice has a ferromagnetic ground state. But the reason why I'm bringing that up, it's very closely related to the way that you're formulating Hartree-Fock theory in terms of this W matrix that you're using. So the way that he formulates his theorem is actually, it looks to me like it's exactly the same as the way you formulate Hartree-Fock, except it's not formulated in terms of single particle orbitals. It's formulated in the many body space. And so if you look at a many body product, if you use a set of product states for your many body basis, it's easiest to see if you think of these as localized orbitals at each lattice site. Then the single particle hopping matrix gets converted into a many body hopping matrix in that orbital space. And similarly, the interaction matrix gets reformulated. If you like, that's just expressing the many body Hamiltonian in terms of those bases. But what he does is he works with writing the wave function for the spin ups and spin downs in terms of a matrix, which I think he even writes as a W. And of course, the fact that it's normalized is that the trace of W dagger is equal to 1. And he then shows this property called spin reflection positivity, which relates to the fact that the ground state has a positive semi-definite matrix that represents the ground state of the system. But it looks like all of the work that you've done in terms of relating Hartree-Fock and looking at optimization exactly translates to the full many-body problem if you looked at it in this formulation. Yeah, I mean, it looks like it's identical. And I just wanted to point that out in case you're not familiar with that.
Yeah, I
You
wasn't
might
familiar
find that
with-
you might find that useful. I mean, it looks to me like it's exactly the same.
Yeah, I'll certainly check it out. I mean, I think it's worth looking at. I mean, at some level, if Hartree-Fock's hard to do the optimization, then you expect doing the mini-body case would also be hard. There's a question in the chat along those lines. It's also asking about multi-configuration methods, whether it's expected that the real value of quantum computing would come from those methods. I think in many ways, the real value of quantum computing, and I think this goes along maybe a bit tangential to this Hubbard discussion, but I think that if we think of when we use quantum computers for anything, right, in many ways we have a quantum wave function. And one of the nice things about having a quantum wave function is we don't need to have a basis or an expression to write it down in. We just need to have the quantum system that just has a wave function, right? So for MCSCF methods, right, or any other multi-configuration methods or any of these mini-body problems, for instance, as you're mentioning in the Hubbard case, the quantum computer doesn't know that it's anything but just the wave function. Right? It's not thinking that this is a wave function for localized system or wave function for these particular types of system from a quantum computing point of view. Right? Obviously, if we want to write it down as matrix product state or write it down as a Hartree-Fock state, then we're going to have some approximations on it. But I don't think that even a ground state problem in that case is not predicated on having a good ansatz or a good description of the wave function classically. Whereas MCSCF methods still require that you have a very short, low rank expression for your wave function in terms of rank 1, rank 2 description. So I don't think multi-configuration methods would be any easier on a quantum computer. In fact, I would imagine even harder because an optimization problem becomes more complicated and you have more parameters and you might end up in these barren landscapes as you go.
Yeah, I wasn't saying that it was necessarily easier, but what I was saying was that it might be that the work that you've done on Hartree-Fock might actually be able to be directly translated into the full problem. That's
I'll certainly read the paper after this. I think it's thank you for the reference.
I think Xiaodi might have had a question. Xiaodi, was there something you wanted to ask? Okay, maybe not. Yeah, so actually, James, so I had one question about these toy models that you described. Is there a way that you can construct an interesting family of toy models where you can parameterize it to larger and larger instances of the problem?
Yeah, for sure. That's exactly what I hope to do with this, because we have this nice landscapes, right? So the fact that we have this landscape, because this is in 2 dimensions, so we can plot it and see it, right? The idea of what I want to do next with this is to actually think of how do we characterize this landscape using the same techniques people use for optimization problems in other instances, right? If we can do that, we get some characterization, we can go to higher parameter spaces. You can think of a very easy family. So for He3+, this is the minimal basis. Or for hydrogen, for instance, is also minimal basis. But the simplest thing to do is use a larger basis. Right?
I see.
We just change M from M equals to one per atom, right? So in this case, the number of orbitals that we have here is just 2, right? But we could do the same molecular system with more orbitals. It'd be a more complicated optimization problem, but it's very easy to grow the problem. There's also a couple of ideas of how to go through the space. So in the case that we have here, we have hydrogen generated at different internuclear separations to generate each one of these energy surfaces. But there's no particular reason we have to stick to hydrogen inside of this basis, right? We could pick a different charge. We could choose different orbitals. We could choose whatever we want and get out different surfaces to give the same pictures, but maybe very different landscapes, right? So how do we actually know how many minima we get out of this based on what the integrals put in are? So I don't know if that answers your question otherwise.
I see. And are there ways that you can construct instances where the number of electrons is also growing? Or like construct a family of instances like that?
Yeah, I think one of the fascinating things about quantum, about this quantum spin fermion transforms, did I mess up? One of the more interesting about the spin to fermion transforms is you think of different number of electrons in terms of spins. If you use something like the Jordan-Wigner transform, then what you have in that case is that you just have the magnetization, total magnetization, but you can imagine simulating it so if you think of it in terms of spin system through a Jordan-Wigner transform, the magnetization is telling you how many electrons you have, and then the number of, if you go to the thermodynamic limit of the spin systems, and that's going to the basis set complete limit of the electronic problem. This thing of infinite number of basis functions.
Mm-hmm.
And so I think the nice thing is that we can construct a lot of families out of this. And I have a lot of ideas about how to construct families to see if we can make families that, so in something like 3-SAT, so you can imagine 3-SAT, it gives a very nice family of problems, right? If you take this ratio of density of constraints, then you get a whole family of random problems. But these random problems have some control parameter that tells you whether the problem's easy or hard. You can talk about phase transitions with respect to this parameter. And so the same question you can ask for Hartree-Fock by taking Hamiltonian families and then controlling this Hamiltonian parameter through some controlling the Hamiltonian path by taking some path through Hamiltonian space. This question here. I don't know what a Floydian quantum trajectory is. So treating as a fluid on a grid is very akin to what people do in density functional theory. You're thinking about density functional, you think of the probability function, it's very much like a fluid, right? So there's some things there I can't answer. I don't know what Floydian quantum trajectory is. Sorry.
Nice. Yeah, I don't know, maybe a related question I also had is, do you think there are ways that some of these quantum algorithms could suggest new classical heuristics for solving electronic structure problems?
Yeah, I do. I think that's actually a really interesting thing, right? So if you go far enough, I think that if this hypothesis that you can always make a algorithm that does what the BQP time algorithm does, I think then that's exactly where you'd have this sort of case that you're describing, right? Because then you take every optimization problem that worked on a quantum computer and try to dequantize it, right? This would be, I think, a very natural thing to try next, right? If you see this VQ algorithm that works, well, just give it some optimizers and they'll figure out how to re-engineer it that you can solve this class of problems. So I think really for Hartree-Fock, in terms of quantum chemistry, there's so much work that's been done over the last 100 years, over 100 years of Hartree-Fock theory, about 100 years of Hartree-Fock theory that people know a lot about where to start your heuristic search, right? So it's probably to start from a whole new ansatz and then figure out what the best place to start the ansatz. How do you get an initial guess for the ansatz? How do you make different optimization procedures for the ansatz? How do you make it as black box as possible? How do you get all packaged into nice packages people can just press enter and run? Is a long way from now, right? And I think as you go along this path, if this hypothesis that you can always dequantize the quantum optimization, then you'll constantly get new quantum optimization problems. Right? If you get new quantum optimization, new attempts at quantum optimizations. So I don't know the answer to that, but I think that it should be.
Thanks. Yeah, are there more questions? Yeah, if not, let's thank our speaker again, and then we can have some more informal discussion after this. Yeah, thanks very much.